and my name is Vadman. I'm a PhD student, and I'm going to be sharing results from my PhD research on the presence of modified circumpolar deep water on the Sabrina Coast in East Antarctica. So the Sabrina Coast is where the Totten Glacier and Moscow University ice shelf system drains an eighth of the interior of the East Antarctic continent. This is equivalent to 3 to 5 meters of sea level rise if all the ice in that catchment were to be turned into water. This is significant because that is approximately the same amount for all of West Antarctica, which Imogen introduced earlier today. The Aurora Subglacial Basin is the catchment for these glaciers, and it is losing mass. These two figures show where the ice surface is lowering and where calving and iceberg discharge are occurring along the Sabrina Coast at the Totten Glacier and Moscow University ice shelf. This process has been attributed to the presence of modified circumpolar deep water at this site, which is a warm water mass that accesses the grounding lines. Keep this acronym in mind, mCDW. It's going to be coming up throughout the rest of the talk. So to get a better look at the Aurora Subglacial Basin, it's AB on this map. It is an overdeepened basin, 1 to 2 kilometers deep. So it's a very vulnerable catchment where modified circumpolar deep water can destabilize glaciers and lead to more discharge. So mCDW is influenced by wind stress, and it can come up onto the continental shelf. The left is a schematic of how mCDW can destabilize an ice sheet, and on the right are actual observations along the Sabrina Coast. So the Totten Glacier is right here, and the Moscow University Glacier here. The deepest red color shows where mCDW presence is most closely coupled with ice loss in this region. So we know mCDW is present today, but in order to put this into geologic context, we need to look at the sediment record. And in 2014, a cruise on the Palmer visited this site. So my aim is to reconstruct ocean and climate changes along the Sabrina Coast over the last 16,000 years, and that's since the last deglaciation at this site. And the importance of this is that it will inform models of sea level rise and ice loss in the future. So we use the sediment record as an archive and the microfossils and molecular fossils within the sediment to obtain their assemblages and geochemistry and predict what the oceanographic conditions were like in the past. This is the actual Sabrina Coast site. So we're over here on the East Antarctic margin, and this orange box is expanded here with the coast and the continent down here and the shelf break and the Southern Ocean up to the north. This is a bathymetric map of the site with the warmer red colors being shallower and the cooler blue colors being deeper. So this continental shelf deepens inland. And our two core sites, sites 1 and 2, are ideally located where the Antarctic slope current comes onto the continental shelf, entraining the warm, deep water mass and delivering mCDW inland towards the Moscow University ice shelf and the Totten Glacier on the Sabrina Coast. These are shipboard observations during the cruise, and we did identify mCDW, this warm water mass at depth from 400 meters down to the seafloor at 600 meters. And these are two sub-bottom profiles of the sediment from our site. So these brown lines delineate where we have Holocene sediment above the more compact sediment from the last glacial. And to get an idea of what these cores are, these short cores collect the sediment-water interface, and these longer cores collect all the way down to the deep consolidated sediment, providing a complete look at the history of this site, as well as providing a lot more material for us to sample. So these are the core logs that summarize the sediment at our site. I want you to focus mostly on this long core, which preserves the deep last glacial sediment with the transition that's very rapid into Holocene biogenic sediment. So this is mostly comprised of diatoms, diatom mud, and diatom ooze. And we have a complementary record from Site 2, and in this long core, we've preserved the same set of units, but just in a slightly more compressed record. But because these two sites are so close together, we can combine these records into a composite, and this is just combining all of these magnetic wiggles that show how much terrigenous sediment versus how much biogenic sediment are in these cores. And for the rest of the talk, I'll be focusing on 3 major sections in these cores, so the corresponding purple shades are from the same units in each core. One of the most crucial steps in looking at a sedimentary sequence is establishing its age in order to convert depth into calendar years, and this allows oceanographers to look at other regional cores as well as compare to global records. And the most important finding in my chronology was that open marine sedimentation began at 15.6 thousand years ago, and going upwards to present through the Holocene, there have been some slight changes in sedimentation rate and a really notable section of high sedimentation from about 11,000 years ago to 5,000 years ago during the mid-Holocene. And to get an idea of what the actual paleo environment was at my site, we use a variety of proxies. The first 2 are probably pretty familiar to people here, foraminifer assemblages in geochemistry that tell us about water mass properties like temperature, salinity, and nutrients, as well as diatom assemblages that can be indicators of sea ice presence or absence, stratification, as well as oceanic fronts. But finally, I'm going to be focusing most closely on the TEX 86 proxy that Imogen introduced earlier. It's a paleothermometer based on archaeal lipid structure. So the membranes adjust their structure based on past water temperatures. And using core tops and current day measured water temperatures, we can create this linear relationship and use the calibration to project down core temperatures back into the past before we could directly measure water temperature. This is a summary of my proxies versus age. So age is along both of these x-axes with sedimentary units. So text, paleotemperature is across the top, followed by stable isotopes of one of my benthic forams, foraminifer assemblage data, diatom abundance data, and that composite magnetic susceptibility. But I'll be focusing on text in these 3 portions of my record. So first, at the deglaciation, there were warm upper ocean conditions present, and you can see preceding this deglacial setting, there was grounded ice over this site, and there was a rapid transition from this grounded ice into an ice shelf setting, and finally open marine sedimentation demonstrated in the diatom data and foram data. And next, in the middle Holocene, which is about 8 to 5.5 thousand years ago, temperatures were quite warm again, almost exceeding 4 degrees Celsius. Diatom and foram data indicated slightly less stratification, and we infer windier conditions based on these indicators. Finally, in the present, there's a very consistent increase in sea surface temperature based on the text. We know present day conditions, there's a polynya in this area, which is a zone of open water over this site, and we know that mCDW is present as well as meltwater. So although temperatures today aren't quite as warm as they were in this mid-Holocene zone, we could anticipate that these may continue increasing as mCDW is delivered to the shelf from these offshore winds that bring water onto the shelf via the slope current. Also, when comparing all of my proxies to a few other records, we have deuterium, which is temperature and atmospheric PCO2 from an ice core in the more interior part of the continent. After the deglaciation, the Holocene seems like a pretty stable and not very exciting period of time, but we know from this text record and oceanic records that these are really important to study because there's much more variability in ocean temperatures than is revealed by atmospheric temperatures. So these are really important proxies to get access to close to the continent. So finally, a summary. We've identified warm ocean conditions during a few periods of the Holocene that we think are associated with modified circumpolar deep water presence on the Sabrina Coast shelf. And particularly, we're interested in this recent increase in mCDW. And this is forced by the position and strength of the Antarctic coastal current, which comes onshore at this site, driven by the southern hemisphere westerly winds. And as far as an outlook, we see that this is significant because the westerlies are projected to shift southward again with continued warming and increasing atmospheric CO2. So we can anticipate further impact of CDW on this site, which could lead to ice sheet instability and sea level rise. With that, I will take questions.